plane wave, a traveling plane wave that we can write down, can be expressed in this form. The real part of a complex vector, which has a complex amplitude, a complex polarization, and the complex phase factor associated with the propagating plane wave. So that's the electric field, and the magnetic field is determined from the electric field according to Maxwell's equations, okay, in free space. So this is a general plane wave in vacuum. We could make it more, it would actually be even in a dielectric medium, as we'll discuss next time. This would be a general form as well, except the relationship phase velocity that gives us a dispersion relation between omega and k will be different, but the form will be essentially the same. This will change as well, of course, because of the nature of Maxwell's equations. So this form, as stated, is for waves in vacuum. And one of the things we talked about last time was that the polarization vector of a plane wave, in general, we represent by a complex vector, and to the degree to which this is a pure polarization, we're not talking about statistical fluctuations of light, we're talking about a so-called pure state of polarization, then that vector could be thought of, you can represent that vector as a point on the Poincare sphere, where the equator of the sphere represents all possible linear polarizations, and the north and south pole are right and left circular polarization, positive and negative helicity, and all the other points on the sphere are some form of elliptical polarization. Okay, and so another way to represent the state of polarization is through what's called the Stokes vector, which is basically the point on the sphere. And since we're talking about pure polarization, it's a unit vector. And one way to write those components is borrowing the language that we may be familiar with in quantum mechanics. This would be, if you want to think about this as the state vector, this is the expectation value of the Pauli matrices. So it has an x component, a y component, and a z component. So in quantum mechanics, we would call this the Bloch vector. In electromagnetics, we call it the Stokes vector. It's the same thing. Okay? All right. The other thing we were talking about last time is for a plane wave, what is the energy density and the momentum density, or the flux of energy. And to do that, we firstly reminded ourselves of a very useful theorem, which says that if I have two functions which are oscillating at a certain frequency, and I want to look at the time average of products of function, then I can easily just write that down in terms of the complex amplitudes of those functions. Okay, it's a very useful little expression. So from that, we were easily able to show that if I wanted to look at the energy density in the field for a plane wave, so the general form of the energy density is E squared plus B squared over 8 pi, time average. Given these fields, we showed that, well, each one of these then, using this formula, was 1/2 this times its complex conjugate. So we wrote this form of the absolute value, which involves both the conjugates. So when I write an expression like E twiddle squared, what I mean is E twiddle star dot E twiddle. Okay? Taking the dot product, the magnitude of the vector and each of the complex amplitudes as well. And since we're a plane wave in vacuum, the magnitude of the electric field and the magnitude of the magnetic field are equal, then the energy density averaged over time is given by this expression. Okay? And that, of course, if I had that form, this parameterization of the complex amplitude is just that magnitude squared, which is really. Okay? The Poynting vector represents the flux of energy, and we call the intensity of the wave the magnitude. Well, I don't want to let's leave this off. Let's call this a vector. Usually an intensity doesn't have a direction, but let me leave it as a vector just to emphasize the direction of that flux. The intensity of the field is the time average of the Poynting vector, and given this expression, that's just c times the energy density in the direction of propagation. Okay? That we always know a flux of stuff, like the flux of charge, we said was the charge density times the velocity of the charge. The flux of energy is the energy density times the velocity of the energy. So that's an expression that makes sense. And finally, the momentum density, G, is S over C squared, is then the energy over C in the direction of propagation. That's the momentum density.
Sorry, what's that symbol you're using?
G. All right. All right. So as I discussed or mentioned in previous lectures, we talk about plane waves. Well, plane waves are not physical states of the field. As we see, the energy density in the field, average over time, is everywhere the same. It's independent of position, which means the total energy in a plane wave is infinite, therefore unphysical. So you say, why bother talking about plane waves if they're unphysical states? Well, as I mentioned, there's sort of two reasons we do that. One is that in some circumstances, we have the wave, the physical wave, is well approximated by a plane wave, at least in some regions of space. So one problem you have for homework is to look at the problem of a laser beam, a Gaussian beam of light, which in the region near the focus of the beam has essentially flat wavefronts, which over the extent of the beam area is fairly plane with a constant phase across the plane. So that's one reason. It's a good approximation. In certain cases, we look at it as a plane wave, and we often do. But in addition, as we mentioned, in the same way that position eigenstates in quantum mechanics or momentum eigenstates in quantum mechanics are not physically realizable states of an electron, they form a good basis for describing a general state. And similarly here, the plane waves form a Fourier basis for thinking about arbitrary waves. So I want to just spend the lecture today talking about the Fourier decomposition, reminding you about some very basic facts about Fourier analysis, which everyone should know. Okay? Fourier analysis is darn important, and everyone should know it. And so if you don't know it, you should learn it more and study it more. So let me just go through into some basics here, just to get your mind remembers some things. So let's just spend just a little bit talking about that. So let's just say we have a signal or some function of time. Then we know that the dependency e to the minus I omega t form, in some sense, a complete set of functions in which we can expand the signal. Okay, that says we can write it as an integral over omega of e to the I, or by tradition in physics, we write it as e to the minus I omega t, weighted by a certain amount of function, which we call the Fourier transform. Now, there is in Fourier analysis, there's all kinds of different conventions here about these factors of 2 pi that I want to remind you of. And the convention we're going to take here, we're going to put the 2 pi in the b omega. So this is in some sense, as we'll remind you why we need to do that somewhere. We could put a square root of 2 pi there and a square root of 2 pi the other. But this is typically the tradition for writing a Fourier transform. So this is f of omega is a Fourier transform. I'll use the symbol script f is the mapping on the function. So this is a Fourier transform. Is equal to the projection of the function on the conjugate, which is e to the plus I. So this is like projecting out the frequency component omega from the signal. Okay, now that factor of 2 pi is got to be somewhere, or some combination of the 2 pi has to be somewhere, because we have the completeness relation. And orthonormality of functions. You recall that if I integrate over all omega, either plus I or minus I of omega t minus t prime, integrated over all omega, this is 2 pi times the delta function. And similarly, if I integrate over all time in the same way, it's obvious that this is. So this factor of 2 pi needs to be there for normalization. Sometimes we write the square root of 2 pi to give it a more symmetric look, but that's a tradition in quantum mechanics. It's not the tradition in talking about signal processing. So I'll just stick with this for the moment. Okay, so this is the Fourier transform, and this is the inverse Fourier transform. Using back the signal. Okay? So, just to remind you of a very simple thing. Let's suppose I have a Gaussian signal, f of t. Got some amplitude that's varying as a Gaussian with some variance sigma squared. Okay? And I want to know what the Fourier transform of this function is. So let's just do that quickly. So we got the formula here. What I have to do is I take the function and I project on e to the plus I omega t. So let's do that. right? So how do I do that integral? Complete the square. So complete the square. Let's just quickly do that. The way I always do it is by I factor out. This becomes minus 2 omega 2I omega t. And I can see how to complete that square.
I think you want square in your sigma square.
Okay, thank you. Indeed. Sigma squared. Thanks. So we got 1 over 2 sigma squared. This is t minus I omega squared. This squared. So when I square that, I get t squared. I get minus 2I omega t. And then I've got to then subtract out the piece that it is, which is, this is going to be minus 1 minus omega squared over 2 sigma squared. Okay, so that's complete the square. Do that in your favorite way. There's a 1 over sigma squared, and that's where that comes from. Yep. Good. I'm glad people are actually paying attention. That's excellent, because I certainly will make mistakes, as you have seen. All right, so we completed the square. This now doesn't depend on t, and so factors outside of the integral. And what's left is dt e to the minus t minus I sigma squared omega squared over 2 sigma squared. Okay? And this integral, well, it's not so obvious you could do that. You'd have to extend it into the complex plane because it's centered at an imaginary number. But actually that doesn't matter. So as an aside, what I always remember, because I used to have this old Deutsch mark which had the normalization of the Gaussian on it, that if I look at the integral of this over all time, it's the square root of 2 pi sigma squared. Because that's the normalization of the Gaussian. And since it doesn't even matter, this could be a complex t tilde, it's still true. So this is the square root of 2 pi sigma squared. That's kind of irrelevant. The point here as a function of omega is that the Fourier transform of a Gaussian is a Gaussian. So the Fourier transform, this is a Gaussian. And the Fourier transform of that is a Gaussian function of omega. This is Gaussian in time. This is Gaussian in frequency. Okay. What is the variance of this function? So here, note the variance, which is well, anyway, I have to normalize it, and that's not normalized. But in this case, the variance of the function was sigma squared. What is the spread in frequencies, or the variance in frequencies, if I were to normalize this?
1 over sigma
1 over sigma squared. That's indeed. Okay. So that, of course, this is a minimum certainty wave packet by the Fourier duality. Okay, very simple stuff that I'm sure you've seen many times. Just wanted to remind you. So let me state a few general properties of the Fourier transform. Let's see. So, first property. Let's suppose f of t is a real function. Then what can we say about the complex conjugate of the Fourier transform? Well, that's a complex conjugate of that. And since this is real, then that doesn't change f, in this case is that, which is the Fourier transform of minus omega. So, if the signal that we're Fourier transforming is real, then we have the following property. The real part of the Fourier transform is equal to the real part of the Fourier transform at minus omega. That is to say, the real part of the Fourier transform is a symmetric function. And the imaginary part, well, the imaginary part of f star is minus the imaginary part of f. So that says the imaginary part of f is minus the imaginary part of minus f. This is an anti-symmetric function of omega. So if my signal is real, then I have a constraint on the one constraint here in the Fourier transform, that the real and imaginary parts are symmetric and anti-symmetric. It's useful to remind myself what else I had to say. Oh yeah, that's a goodie. The convolution theory. So, let's consider the Fourier transform of the product of two functions. Okay, so that's equal to f of t, g of t, e to the I dt. Okay. So now we can plug in for one of these guys. Let's plug in for f of t in terms of the inverse Fourier transform, f tilde e to the minus I omega t. We do, thank you. That's right. Yes, indeed, that's absolutely important. This is a dummy variable. I knew something was going on that was giving me shivers. It helps, right? Because omega here is fixed, and this is a dummy variable. Don't use your dummy again. Okay, so now that's good, because now I can write that as d omega prime f tilde of omega prime, the integral dt g of t e to the I omega minus omega prime t. And this, of course, everything is integrated from minus infinity to infinity, is equal to g tilde evaluated at omega minus omega prime. So we have the convolution theorem says that the Fourier transform of a product of functions is the convolution. Since this is now a dummy variable, I'll change it back to omega. Between the two functions. So this is what's called the convolution. Convolving two functions together. Okay, you shift one relative to the other and integrate over the shift variable. That is the convolution. And similarly, the inverse Fourier transform of the product of two Fourier transforms is the convolution of the signals. Important result. Next, translation dual with phase shift. What do I mean by that? So let's look at a Fourier transform of a shifted function, shifted by some amount t naught. So if I look at that, I put f of t minus t naught here, well then I can just redo the variables and that causes a shift of the phase. So the Fourier transform of a shifted function is a phase shifted version of the Fourier transform. And similarly, if I shift the spectrum, then the inverse Fourier transform is a phase shifted version of the signal. So a shift in the time domain is a phase shift in the frequency domain and vice versa. A shift in the frequency domain is a phase shift in the time domain. Let's see. Next, last, and most general thing I want to say here is about Parseval's theorem. So Parseval's theorem says something about the total integrated this is a kind of inner product. We thought about this in kind of quantum mechanical terms, thought about this as a psi and a phi. This is like the inner product between the two wave functions. Here I'm allowing more generally f and g to be complex signals. They could be real. In those cases, we can make a difference. Then we know, sort of, I can take the inner product in position space or in momentum space. So it's obvious from what we remember from quantum mechanics that with the right measure on the integration, that I could take the inner product in the frequency domain and it would be the same. That's called Parseval's theorem in Fourier analysis. Okay, so let's do an example. want to talk about quasi-monochromatic pulse. Okay? What do I mean by that? Well, monochromatic means one color, one frequency. So quasi-monochromatic means almost one frequency, but not quite. So what we mean by this is the following. I have some finite duration pulse. It's not an infinitely long wave train, which we said was unphysical. So it's got a finite duration. It's supposed to be a Gaussian. And then we have this oscillating field. Supposed to be the same frequency. Not so bad. Okay, so this, what's supposed to happen is that there are many, many oscillations. This pulse has a particular width to it, delta t. Of course, there's the period of oscillation t. So let's look at the specific example where my pulse is a form of a oscillating cosine that's modulated in amplitude by a Gaussian of width delta t. Okay? So this is like amplitude modulation. I don't know if you guys are too young to remember AM radio, but AM stands for amplitude modulation. And I'm looking at the case where this is a Gaussian modulation. Okay? So omega t here is 2 pi over omega naught. That's the period of this. This is sometimes known as the carrier wave. This is radio language. So this is, 1550 megahertz, your gap carrier, and then your mono AM. All the signal is modulated here. This is known as the envelope. This is the envelope of this pulse. Okay. So all the signal is on this carrier. So the question is, what is the Fourier transform of this signal? Well, we can do it pretty darn easily. So this is the Fourier transform of this function, which I will write cosine as e to the plus I omega t plus e to the minus I omega t. So this is A. Actually, let me do it in a slightly different way. Sorry. There's a very simple way to do this, and let me emphasize that fact. We can think about this as the product of two functions and use the convolution theorem. So the Fourier transform of the product is the convolution, which I'll write convolution as the made-up signal star circle. This is the convolution. So I need to convolve the Fourier transform of this with the Fourier transform of that. Well, we just found the Fourier transform of this, right? So let me call this thing what should we call this? Let's call this g of t. So g tilde of omega we just found. Okay. What is the Fourier transform of this? It's two delta functions, right? I mean, we can see that easily if we just write it out quickly. The Fourier transform of this, e to the I omega t plus e to the minus I omega t over 2, that's cosine. We have to multiply that and integrate. Okay? So this is equal to 1/2 dt e to the I omega plus omega naught t plus e to the I omega minus omega naught t, which is 2 pi times the delta function there and 2 pi times the delta function there. So that's pi delta omega minus omega naught plus delta omega plus omega. Okay? What about the convolution? So now we have to take the convolution of this function with the delta functions, right? So let's do a little aside. What is the convolution g of tilde with the delta function, say, centered at omega naught? Well, according to that, that's the integral g omega prime g tilde over 2 pi omega minus omega prime that's the convolution integral. And what's the answer to that? It's g tilde centered at omega naught. In this case with those units. So, what do we have here? The Fourier transform of our quasi-monochromatic field is equal to some constant that I really don't care about. Square root of 2 over pi a, and then e to the minus all right? So, I didn't actually emphasize the fact here, what does it mean for this pulse to be quasi-monochromatic? Well, this isn't necessarily the best picture in the world, but to be quasi-monochromatic is to say that the length of the pulse is huge compared to one period of oscillation. Why does that translate into almost one frequency? Well, we see that in the Fourier transform here. What does the spectrum look like? If I plot this as a function of omega, what does it look like? Well, it's two Gaussians in omega, one centered at plus omega naught, and one centered at minus omega naught. That's where the centers of these Gaussians are. And what is the width of each of these Gaussians? 1 over delta t, or the variance of 1 over delta t squared. So what I have here is two peaks that are Gaussian that have a width, delta omega, that's on the order of, well, in this case, is equal to 1 over delta t. So, if delta t is huge compared to t, which means that delta omega is tiny compared to the carrier frequency, then the width of these peaks is much narrower than the distance between them. If my pulse was very long in duration. So as you know, you have this Fourier duality. A long wave train means a well-defined frequency. As I make the wave train pulse narrower and narrower and narrower, I have a broader spectrum of frequencies. This will spread out more and more and more. There's an inverse relationship between the length of time of the wave train and the spread of frequencies, right? And as delta t goes to infinity, this becomes delta functions, which would be the case of infinitely long wave train. So the most general form, if I had not just Gaussians here, if I have a wave train or a general AM modulation, f of t is equal to g of t cosine maybe not, then the Fourier transform of this is equal to g tilde e plus g tilde plus omega with some constant out front that I'm not caring about. So right here we had g tilde is a Gaussian, one centered at plus omega naught and another centered at minus omega naught. All right? Okay. So, I hope most of this is pretty darn familiar to you, but again, I would review it if it's not. We can discuss it more. All right, let's come to the front board then. So what we talked about here has nothing to do with the input per se. It's about Fourier analysis, which we now want to apply to the context of electromagnetic waves. And so the question is, what changes? What do we have to think about in a special way when we're talking about electromagnetic waves? Oops. All right, so let's talk about application to electromagnetic waves. Well, there's a few different things we need to talk about. One, we're talking about waves in space, in time, and space. So at the moment I just talked about functions as a function of time, but the wave is also a function of position. So we need to think about the Fourier analysis in both time and in position. We're talking about vector waves. So we're talking about not just a scalar function that's a wave. We're talking about a vector function that's a wave. We must satisfy Maxwell's equations. Maxwell must be satisfied. You cannot deny Maxwell. Even plural. All of them must be satisfied. And yeah, well, that's kind of it. So, how can we do that? Well, we need more board. Okay. So, we can write down an ansatz, because what we can do is, we know we have the Fourier theorem, which holds true for time, but also holds true for x and y and z. So we have, in some sense, a four-dimensional function, a function of four variables, x, y, z, and time. So we can write down a four-dimensional Fourier integral. And so that's what we're going to do. My general vector to start with is an integral over omega dkx, dky, and dkz, which we write as d cubed k. And then with these units, I have a 2 pi to the 4th. And better chalk. Best we can do. So then we're going to integrate e to the minus I, or actually, yeah, so we're going to superimpose the inverse Fourier transform. And by convention, we do this e to the I k x x, e to the I k y y, e to the I k z z, with the plus sign for the spatial case. And then we have to have the Fourier transform. Now, we have to satisfy Maxwell's equations. So we can do this because what I just erased, stupidly, was the plane wave vector that satisfied Maxwell's equations in vacuum. So this is going to be a wave in vacuum. So we have some complex amplitude which depends on this particular omega nk. Complex. That's my Fourier transform. However, it's got to be a vector. It can't be a scalar. So we got to stick in a polarization vector. Of course, that polarization vector depends on the direction of propagation because it has to be transverse. And there are two different ones that are possible that are transverse. It could be horizontal and vertical, or circular. But we have to have two different polarization vectors. So the sum over mu being either whatever two indices we like for vectors. Yeah, I think that's it. That's what we got. So there it is, where, and of course, B, once I have E in free space, I got B. E and B are constrained by Maxwell's equations. They're not independent. So it's the same thing, except it's got exactly the same amplitude, but the direction is the opposite. You know, it's the perpendicular thing. So everything else is exactly the same. It's the same function here. And that's it. However, that's not, there's one last piece of information. Omega and k are not independent because of the dispersion relation. So in order to satisfy Maxwell's equations, we know that omega squared has to equal c squared times k squared. So we have that constraint. That's the dispersion relation. So now we're done. Okay. So, okay. So now, let's try to simplify this a little bit. Let's just look at E and B is as written. The delta function has two roots, omega equals ck and omega equals minus ck. They correspond to waves propagating in different directions for a given k vector. So now we can do the integral over omega, because omega and k are not independent. So let's do it. Tedium, dqk over 2 pi of d tilde omega equals ck. Remember what this means. I should write this out more. This was the magnitude of the vector squared. So c is the magnitude of the vector and a function of the vector. There's 2 pi goes to 2 pi to the 4th. The polarization vector, which depends on the direction of propagation, e to the I k dot x minus omega t, where omega sub k is c. Okay. That's integrating this first delta function. And then we have the second delta function. Boring, boring, boring. Sorry. Can't think of a simple way to do it except writing the whole thing out. But let's do it. Omega equals minus c times this k vector omega 2 pi epsilon tilde k hat e to the I k dot x plus omega k. All right? So, these things have names. Alice and Bob, no, that's not their names. This is called the positive frequency component. And this is called the negative frequency component as a function of. Why is that? Well, you can kind of see that here. Let's go back to this board. We see that when we have any signal, it's composed of frequencies on the positive omega axis and the negative omega axis. So these are the positive frequency components and the negative frequency components. The positive frequency components, by our convention, because we love to confuse things, go like e to the minus I omega t. And the negative frequency components go like e to the plus I omega t. And that's what we see here. These frequency components all go like e to the minus I omega t, and these frequency components go like e to the plus I omega t. So this is called the positive frequency component. And this is called the negative. Now, my next task is to convince you that the negative frequency component is nothing more than the complex conjugate of the positive frequency component when the electric field was a real vector, a total electric field. Okay? So, to do that, I'm going to annoy you to no end and just use the board to erase things. Maybe the annoyance will end, but probably not the rest of the lecture. Okay, so what am I going to do? Well, let's do the substitution. Since we're integrating over all k's, I can set k to minus k and integrate over that as well, the same integral. So I'm going to set k to minus k, and then the integration is exactly the same. Okay. So now, I have to set k to minus k there as well. So, what is this? Well, now I can factor out a minus sign. And from one of these lovely, well-prepared properties that we have of the Fourier transform, which says the Fourier transform, if I set all of its arguments to minus, if the overall vector were real, maybe I won't do the erasing, e of minus omega and minus k is the complex conjugate for any u. Of course, this could be for a different u. We should say each polarization has its own amplitude. I really should have put that in. That's only fair. I don't want to cheat, make the same amplitude for both. That's way better than that. But this is true, right? That's one of these properties. The other thing that you can see is that this is equal to that. If it were linear, it wouldn't make a difference. I have a linear wave, if I look at its, if the wave vector is in this direction, and the polarization vector is that direction, put the other direction, it's the same polarization vector. But for circular, then it's, that's the conjugate. It's relative to the k vector that we're defining the helicity. So, that's nice. Star. Star. Et voila, E minus is the conjugate of E plus. So, this is the general form of the Fourier decomposition of the wave into its modes. This plus complex conjugate. Notice there's one very tedious thing here. I mean, this is like what we talked about with the complex amplitude. For the complex amplitude, we wrote down for a single plane wave, it was the real part of something like this, right? When we just had one plane wave, we wrote it as the real part of an amplitude, a polarization, plane wave. Well, the real part is something plus its complex conjugate over 2. So there's these horrible factors of 2 that are floating around when you deal with positive and negative frequency components versus real and imaginary parts. Just a little warning for you that comes up from time to time. And of course, B for the plane wave is the same thing, but with a k hat crossed into u. Exactly the same. All right. Now, one example I just want to talk about briefly is where I'm talking about propagation along 1D. It's called the z-axis. This general form allows for propagation along any direction. Let's restrict our attention to one spatial dimension and one time dimension. So let's go back to the form that was over here where this had this delta function and write that out again. I'm going to have 1D with polarization epsilon. So E as a function of one spatial direction called Z, got one polarization, d omega dk d tilde omega and k, e to the I kz minus omega t delta squared c squared k squared. Now, in this case, I can think about it the way I've written it. I have a choice. In this case, of course, let me write this out a little bit more explicitly. Both of these go from minus infinity to infinity. I can integrate over k, or I can integrate over omega. I have a choice. And either of those choices are useful in different circumstances. Let me write them out. So I have choice 1. Let me borrow my notes just to speed this up a tiny bit. So if I integrate over k, leaving the integral of omega as undone, I have this expression for the wave. Okay. Choice number 2, I do the integral over omega, taking off the delta function, and leave the integral over k in the general form. Let's write that out as well. What can we say about these two forms? Well, in either form represents the wave over all space and time. In one case, it's related to some function of omega. And then for each function of omega, I have something which propagates me forward or backward in time. Or I have some function of k and something that propagates me forward or backward along the z-axis. This is a propagation that takes z to different z's depending on the time. And this goes backward the other way. And in this case, I go forward or backward in time. So the solution to the wave equation is a PDE, and depends on the boundary conditions and the initial conditions. So, the two forms correspond to two different boundary conditions. For example, in case 1, suppose I'm given the electric field at the z=0 point as a function of time. And I'm also given the time derivative of the electric field at z=0 as a function of time. So for example, suppose I have a microwave generator. I have this horn that's going to spit out microwaves. And I attach this to some voltage source as a function of time, which creates some oscillating antenna, which is going to oscillate as a function of time, and this is at z equals 0. Then I can propagate this forward to later positions using form 1. On the other hand, I might have a different situation where for form 2, what I'm given is at the initial time, I'm given the field everywhere along the z-axis, and I'm given its derivative everywhere along the z-axis at the initial time. This is the initial time problem as opposed to the initial space problem. So I might say, okay, here it is along the z-axis. There's some pulse that has some funny shape. And what's going to happen is some of it's going to propagate along this direction, some of it's going to propagate along that direction. I'll get some, funky thing going at the speed of light in the positive and negative z directions, depending upon the derivative as well, how much it divides up. I'm sure that's a problem you've seen in simple P's, where you start with initial pulse and you let the thing just propagate and it splits up into 2 directions. But I can also have a different situation where I know what it is as a function of time for all times, but at a fixed position. That's a more natural problem when I have an antenna. All right? Okay. All right, so one last topic I want to discuss about plane waves in free space. So we talked about energy and momentum for a plane wave in free space. What about energy and momentum for an arbitrary wave in free space? Well, our handy-dandy Fourier decomposition gives that to us. So what I want to say is, what is the energy momentum of an arbitrary electromagnetic wave in vacuum? Not necessarily a plane wave. We have written here the general form of such a wave as a Fourier integral over plane waves. And so it is a trivial business to write that down, because we know what the energy and momentum are of each plane wave. Thus, the energy of the total wave is just a superposition of the energy in each of those waves. So we use the Fourier decomposition. So let's look at the energy. The total energy in the field is the integral of the energy density let's look at the time average version of that. The energy in the electric field for each plane wave is the energy in the magnetic field, so we can write that each one contributes equally. E and B are equal, so we just add them up. And now we can express this in terms of the positive and negative frequency components. The average of E squared is the average of E plus E minus squared. But when I time average, the E plus and E minus average to 0. So what I get when I have the E plus squared with E minus squared, that will average to 0. So all I get is I get the average of E plus divided into E minus, and I get 2 copies of that, because the other one's time average to 0. Right? Because they're going to go like e to the minus I omega t square that 0. What you got to have e to the plus I with the e to the minus I in order to average that to something that's not 0. Okay, so we can plug that in.
You mean D3x?
I do, thank you. And then I have 2 copies of that.
When we were finding the magnitude squared of E plus
Yeah.
those are complex vectors, I think, so that we have to put the complex conjugate on one of them.
One is the complex conjugate of the other. E plus is the complex conjugate of E minus.
Yeah, so that would probably simplify things.
Okay.
Okay, so
All I'm
right,
saying,
because the sum is real.
that's right, this sum is real. This sum is real. And this is real. All I've done here is, maybe I should write this out in more steps. This is the E plus E minus dotted into E plus E minus. Okay? These are complex.
Right.
Each one of these are complex. I can think about this as twice the real part of this.
Right, okay, it's because the 2 vectors that you're dotting initially end up being real, so you never have to take the conjugate.
That's correct. This itself is real.
Yeah.
So I just multiply it by itself, not itself. And that time average is equal to that.
If you did take the conjugate, then wouldn't it end up like the same thing?
Okay, let me try to be clear here. Of course, you have to make a difference. We had, at the beginning of the lecture, we discussed a hand-in-hand theorem, which said that the time average of the product of 2 functions was equal to twice the real part of their complex amplitudes. I mean, 1/2.